Hi my dears, Uncle Dummy, here I am. How are you? Methods of irrigation is our first subject, which including the practical applying watering methods to plants in the field. Indeed, choosing of the suitable method depends mainly upon many variables such as source of irrigation and its quality, types of crops and its characteristics, climate, culture and behaviors of planters, and the available investment at speed. Let us see together. Generally, the ideal choosing for irrigation method should fulfill the following requirements. My dear, it is so easy to follow up by yourself. Take in consideration that applying good suitable irrigation method is very important because it is meaning achievement a high additional efficient of water on all the parts of field, and so obtaining in good yield and conservation the capital investment. Side by side, the excess of irrigation, which may applying gradually causing several problems and effect on the soil characteristics and yield. Figure showing the general plan of different methods, systems, and types of field irrigation. Take in consideration that field irrigation method divided to two main categories, which is known as gravity irrigation and irrigation under pressure. And also, each category divided to subcategories as shown in front of you. The rest of previous figures, look my dear, it is very important and we'll discuss after in detail. My dear, we'll divide this subject for simplify to 6 parts A, B, C, D, E, and F. Part A, gravity irrigation. Gravity methods such as flooding, furrows, corrugation, border strips, and basins are the cheapest applying methods when conditions are suitable to install one of it, because it is need to just applying water direct to the field plot from an open ditch located at the upper head of the field. Usually, gravity irrigation methods are accomplished by sequence stages as initial advanced discharge flow down the slope. Wetting period as the whole of run should be wet by water after completely cut off water supply. Anyway, selection of the most appropriate gravity method is very important step and depends upon many variables as shown in the enclosed table, which you can get it as a guide for you. Table showing the selection guide of gravity irrigation method. You can follow up easily. Fooding irrigation method is the method which allowing to flow water from an open ditch directly to the field plot and leaving water moves and guides without any control on the soil surface. It can be applied by or generally flooding or under control. Free flooding irrigation is the method which allowing water flow free without any restriction. Anyway, this method normally requiring much manual labor and has low application efficiency and low moisture distribution uniformity also due to the random distribution of water on the soil surface. Figure showing free flooding method. As you see, non-uniformity distribution of water on the soil surface. Contour ditches flooding method can be applied in irregular topography land where furrows, borders, and basins technically are not visible. Anyway, this method is often used under planting density crops or furrows on slopes and at cases where can't be easily leveling the land, as shown in the enclosed figure. Furrows irrigation method is a common way in most countries and mainly used for row crops such as maize, cotton, tobacco, groundnut, potato, sugarcane, and also for orchards by broadening the spaces between furrows. In this method, water weight about 20 up to 50% only of the soil surface area, and thus verify less evaporation and less puddles, and consequently obtaining a good air-water balance than under the flooding method, as shown in the enclosed figure. Furrows should be designed and operated properly to achieve a good application efficiency and moisture distribution in furrows. This method occupies area and requires a continual maintenance and a larger discharge drainage area than sprinkler or drip method. Moreover, the infiltration rate decreases under continual irrigation by this method, so the experience and skills of users are very important in making the necessary periodically all irrigation and adjustment operations. Generally, height of furrow bases varies from 15 up to 40 cm, which mainly controlling its water carrying capacity as shown in the enclosed figure. Distance between ridges should be based on the optimum crop row spacing and accommodate the track of machinery equipment. Usually, light texture soils have closer furrow spacing than heavy texture soils. Usually, the common furrow spacing are varied from 0.3 up to 1.8 meter and is averaged around 1 meter. Anyway, alteration of furrow space are very important also under saline conditions to avoid the accumulation of salt pockets and consequently decreasing the harmful effects on plant growth and crop protection, as shown in the enclosed figure. Figure showing alteration the furrow shape for salinity control, really for allowing to lead the accumulation of salt pockets. Generally, to avoid the high cost of land grading and a case of applying furrow irrigation method, it is good for applying the contoured forest gibbous as shown in the enclosed figure. Choosing the optimum furrow length in the field is very important. Otherwise, problems of deep percolation and runoff will occur. Deep percolation will affect on losses of water, leaching of nutrients, water logging, in addition to aggravate the problems of drainage system in the area. Furrow lengths should be estimated practically under the local field conditions to obtain more accuracy, but generally we can follow roughly the enclosed table. Guide table for suggestion furrow lengths per meter under different slope percentage, soil texture, suitable flow at upper head, and water application depth per millimeter. Look, my dear, it is a good table. Practically, furrow lengths can be estimated by choosing a 3 long parallel furrows and fixing an observation station on each search distance along it. Take into consideration that the initial moisture and the inflow rate must be the same for all the 3 furrows. Outflow should be measured at the observation station of the middle main furrow by fixing a small slope or V-notch as the average elapsed time of reaching the waterfront to be different observation station along this middle furrow. Accordingly, a graph of the intake rate per liter per minute again is the average elapsed time per minute for the furrow is then constructed on log paper. Hence, all the slope intake line N and the intake rate at 1 minute K can be defined as shown in the enclosed figure. Figure showing furrow intake rate with time on log paper as described before. Scientists cradle suggested that the waterfront should reach the lower end of furrow within a time equal to T divided by 4, where T is the required time per minute. Because at this point we'll obtain a good moisture distribution uniformity in the root distribution zone along the furrow length, as the deep percolation losses will be non-significant, less than 5% at this case, as shown in the enclosed equation. Table showing the intake rate per liter per minute at 30 meter of furrow length at various average lapse time depend upon the data obtained from the field experiment. As shown, the required time t for infiltration and application depth t in millimeter for furrow length equal to 30 meter, while its width equal to 1 meter can be calculated by substituting the enclosed equation, taking consideration that n equals minus 0.5. Figure showing the relation between the elapsed time t per minute against the distance down run per meter. Hence, the furrow length can be chosen with the waterfront advantage in time equal to t divided by 4 from this curve. Supposable the desired application depth d equal 40 mm, and by substituting the enclosed equation, then t divided by 4 equal 37.516 minutes. And also, the actual application depth can be confirmed mathematically, which is equal to 3.8 cm as shown. Then, the choosing calculated length is right, and we'll get a good motor uniformity along the furrow run. Suppose we choose the furrow length to be either 150 or 180 meter, hence the application depth is equal to 5.98 centimeter at case of 150 meter length, and equal to 8.02 centimeter at case of 180 meter length. These calculated application depths are more than the other one. Accordingly, the moisture distribution along the furrow run will be not homogeneous uniformity as this case, which means more deep percolation and puddle will occur at the upper head of furrow, while it's expected to obtain less percolation than the zeros at the lower end of furrow. Moreover, may be actually not true. Soil Conservation Service (SCS) designed models depend on the availability of many input parameters, such as soil intake characteristic and classification into SCS intake family. Flow, the hardness coefficient by many equations, feed dimensions, available discharge as the feed inlet, requirement application depths, and other information such as irrigation practice, soil physical characteristics, irrigation drainage water quality, soil salinity, water table level, crop rotation, and the maximum expected water requirement, water deficit, and so on. Intake family equation and its parameter referring to soil conservation service as shown. Table showing the function parameters for soil conservation service SCS intake family. A range of possible furrow flow rates should be tested. Low flow rates will result on increasing the water advance time, hence non-uniformity of application and losses by deep percolation will be occur, while a high flow rate will cause erosion and overtopping the furrow ridges also. Thus, the furrows must be large, deep, and well constructed, and good tillage in addition to maintenance of furrow cross-section through the planting season is recommended also. Accordingly, and for more accuracy, the optimum flow rate will be obtained practically for the furrow by field trials. Water can be applied to furrow either directly by direct opening or under control by using one or more devices such as multiple siphon tubes, gated pipes, or riser pipes. Siphon tubes, which should be placed over the side of these pans, take into consideration that water level as the irrigation supply ditch should be at sufficient height above the level of furrow. Siphon tubes are generally manufactured from reflectable materials such as plastic or aluminum in order to be light, weight, easy use, and in a different diameter such as half, 3/4, 1, 2, 3, or 4 inches, as one or more tubes can be used to serve each furrow, as shown in the enclosed figure after. Figure showing siphon tubes and its installation way. The discharge Q of a given siphon tube is the function of the operating head H, which is the difference in level between the water surface in the supply ditch and furrow above the end of tube. Anyhow, values of Q as a function of H for different diameters are generally finished by the manufacturing company as shown in the enclosed paper. Table showing the discharge of siphon tubes per liter per second as a function of operation head H under different diameters. Gated pipes are made of aluminum to become popular used in furrow irrigation method because no need for dishes as scarce, saving labor, high efficiency, and on the other hand, requiring less energy. The gated pipes have light weight and so can be carried easily to different positions in the field. The pipes are generally had 110, 160, or 200 mm diameter, depending upon the length and their discharge, with erection orifices on equally spacing along each side, while each orifice having one furrow. The orifices are provided with slide gate that can be adjusted to the regulated desired discharge, as shown in the enclosed figure. Figure showing gated pipes with its orifices on equal spacing. Riser pipes, which consist of paired supply pipes, conveys water under low pressure to equally spaced riser pipes. Water is delivered to furrows through perforated orifice in each riser above the soil surface. Each orifice specialized for more than furrows and are providing with a slide gauge to adjustment the designing discharge, as shown in the enclosed figure. Corrugation irrigation method. It is a modified of furrows method having the same principle. Corrugation have smaller cross-section than furrows, which features like shallow furrows. Its depths vary from 8 up to 12 cm, while its length is around 100 meters, and the spaces in between are closer and varies from 0.4 up to 0.6 meters, as shown in the enclosed figure. Basins irrigation method. It is a common method of gravity irrigation, especially in clay and loamy texture soil. The field is divided into small plot basins, surrounded by ridges or levels around all its sides, have 20 up to 30 cm high. The size of basins depends mainly on soil texture, available input stream discharge, type of plant crops, and the required depth of application water. Generally, basins have square or oblong shapes and are suitable for close-growing crops such as wheat, forage, rice, and so on. Sometimes also using to irrigate orchards such as citrus and banana, as shown in the enclosed figure. Figure showing basin irrigation method as case of field and orchard crops. Border strips are strips of land separated by parallel borders or levels. Its size depends mainly on soil texture, slope, and the fluid discharge. The main problem is the trend of water moving side down and non-uniformity application as a result of existing any cross slope along the strip, as there are no ridges to restrict the lateral movement of water. At the same time, it is necessary to use the optimum flow discharge as the upper head to allow for a complete transverse spreading of water sheet during the irrigation time along all the length of strip, as shown in the enclosed figure. Figure showing normal and contour border strips irrigation method. Table showing the suggested optimum strip width as related to its length and flow discharge under different soil texture, slope, and water application depths. Look, my dear, it is a good guide table. Longitudinal slope should be also allow for a rapid spreading of water flow from the upper head down the predominant slope towards the lower end of the strip to obtain a good longitudinal motion uniformity as possible, as it is ranging between 0.2 up to 1%, depending on soil texture and flow discharge surrounding border. Ridges also should be height enough, ranging between 20 up to 30 centimeters to be more sufficient establishment and withstand any erosion process, in addition to keep the water stream limited inside the stretch. Table showing the suggested maximum safe flow irrigation discharge per foot of border strip width. Look, my dear. Water management of border strip differs than furrow method because of using large discharges scales. With advanced water sheet reaching around 70 up to 80% of the strip length, the water supply should be cut off and start for recording the time of recession water sheet at each station, in addition to note any runoff which subsequently occurs at the lower end. To achieve a high distribution uniformity and less deep percolation, the recession curve should be light above the entire curve and close to it as possible. On the other hand, if the recession curve lies under the irrigation curve, it means the strip is still under irrigation downstream, and hence the time of irrigation is still non-sufficient and so need more time of flow. Figure showing the efficient border strip irrigation and good moisture distribution uniformity. Note, my dear, the recession curve lies above the irrigation curve and close to it. Note, my dear, if the flow source is cut off, when advancing water sheet has covered about 80% of the strip length, the result would be an excessive deep percolation upstream, while an under-irrigation downstream will occur. Cutting off the flow area or later can't improve the moisture distribution uniformity in this case, as area cutoff will reduce the deep percolation upstream and increasing the area and degree of under-irrigation downstream, while lateness of cutoff will result in the opposite effect, as shown in the enclosed figure. Figure showing the border strips with excessive deep percolation and low moisture distribution uniformity. Note, my dear, the more deep percolation and the under irrigation area downstream. Figure showing the case of border strips with under irrigation case and non-moisture uniformity with excess of water runoff. Note, my dear, there are many factors which should be taken into consideration when designing border strips such as soil texture, crop species, land slope, and flow discharge. For a given slope and width, each of flow discharge, length of strip, and the suitable time of cutoff should be experimentally accurate. Selected is necessary to achieve a high irrigation efficiency. Table showing the soil intake rate and accumulation date by using double range spectrometer as practical field experiment data done by scientist Corrugation. Note, my dear, that the mathematical calculation is clear down table. Table showing the rates of previous calculated data at the two trials of both long and short strips. Table showing the accumulated required time per minute for applying the desired application depth at the two trials of both long and short strips. Figure showing the intake rate curve as a result of field experiment data. Figure showing the advanced and recession curves as case of long border strips. Figure showing the advanced and recession curves as case of short border strips. Look, my dear, it is clear on the first trial that 51.69% of additional water was lost by percolation because there are no runoffs, and so the application efficiency was 48.31%. On the other hand, it is noted that at the second trial, the application efficiency was increased to be 80.81%, which is meaning that 19.19% of additional water was lost only by percolation, as there are no runoff notes during the two experimental as shown. The mathematical calculations of the application efficiency at both trials long and short lived, followed by the sun. Note, my dear, for conclusion, it is noticed that as the first trial case, the problem can be solved by two ways, either by increasing the inflow discharge so that water sheet can reach the lower end of the stream more fast than before and so cut off the area, or shorten the length of border stream. Indeed, there are many design procedures that are introduced by many researchers, such as Soil Conservation Survey (SCS), Walker and Sherber, and Wanhu, concerning the mathematical calculation equations of needed irrigation time of border streams. By using Soil Conservation Survey (SCS) design method, the designer usually seeks on the appropriate strip widths for the input basis. SCS level border strip design model depend on the availability of many input parameters such as length of run, intake family and function parameters, management value, and requirement application depth, total available flow practically in the site, and minimum desired value application efficiency as shown in the enclosed equation. Table showing the function parameters for SCS intake family. However, for designing border strips, there are some constraints must be checked out, such as ratio of inflow time to advantage time should be more than 0.5 for clay soil and more than 0.75 at case of sand soil. Maximum flow depth for the unit dot stream is calculated, hence the minimum pond height is recommended to be equal to this maximum flow depth plus a freeboard of 3 cm, and a relatively large stream is needed for efficient level border irrigation, hence allowing 2 or more turn-out per strip must be taken into consideration to prevent any erosion. Usually, level border steps are constructed by forming ponds or tanks, which must be high enough to contain the maximum expected flow depth, with a freeboard of at least 3 cm. Moreover, often a small ditch or furrow adjacent to the pond and on either side will be formed as a result of construction process. A guide table showing the relation of advanced time to opportunity time for various values of application efficiency. Subsurface irrigation method is a way of applying water directly to the root distribution zone of plants through a series controlled open ditches have 50 up to 100 cm depth, 30 cm width, and 5 up to 10 meter spaces in between, which depend on the soil characteristics. Sometimes, a parent perforation pipes or hoses under suitable pressure can be also used instead of open ditch system. As this case, pipes should be placed at narrow spaces around 1 meter and shallow depths of 50 cm or more. Generally, there are many favorable conditions of applying subsurface irrigation methods. Follow up by yourself, my dear. It is so easy and clear. Goodbye.